All right, good morning, 11th grade. I hope you're doing great today. This is going to be your notes video for this week. I know you guys were probably sad thinking that you weren't going to get any notes this week, but never fear, I got your back. All right, so with this week, we are starting a new chapter, chapter 16. You can find it in your textbook on page, I'm going to say it's 268 maybe. But you can find it there and check it out, check me up, see if what I'm telling you is true or not. But anyway, chapter 16, we're going to go through the first section of notes in this video, and that's going to be your notes video for this week. Next week, hopefully, we will cover sections 2 and 3 in our notes video because they're shorter sections, so we're going to combine them. If you have any questions, shoot me an email, post something on the LMS, and I will do my best to answer your questions, all right? So, chapter 16 is Oxidation Reduction Reactions and Electrochemistry, or what I like to abbreviate, use the abbreviated form, redox reactions. That's what we're going to be looking at for the first portion of our notes. Section 1 here is the oxidation reduction process, or redox reactions, why they happen, how they happen, and how different elements behave in oxidation reduction reactions. Okay, so some basic introductions here for you, some basic terms that you're going to need to be familiar with. Again, make sure you are taking your notes down, okay, because I am going to be checking your notebooks when we come back, making sure that you are up to date on your notes, and that's going to be a quiz grade, so don't skip this part, okay? So, oxidation reduction reactions, or redox reactions, like I said, these are chemical reactions that involve a change in the electron configurations of the reacting substances. So, matter and energy is neither created nor destroyed, right? But it can change forms and it can change positions. So a redox reaction looks at the change in positions of electrons. Were they traded between substances? Were they moved around inside the original element, okay? And that's what a redox reaction is going to focus on. So oxidation is the process in which an atom loses one or more electrons, okay? So oxidation, electrons are being given away, okay? Or in some cases taken away. Either way, the atom is losing at least one electron, but it could be 2 or 3 more, depending on the substance doing the losing and the taking, all right? So an abbreviation to help you remember this is LEO, a loss of electrons equals oxidation, okay? You see the L for loss, E for electrons, O for oxidation there, okay? So a loss of electrons equals oxidation, or LEO. Then we have reduction. This is any process in which an atom gains 1 or more electrons. So oxidation, they're losing them or they're being taken from them in some cases. In reduction, the atom is gaining electrons. Either A, it is doing the taking, so it's getting electrons, or B, it is accepting orphan electrons pretty much, okay? So GER is a way to remember this, G-E-R, gain of electrons equals reduction. You can see there G for gain, E for electrons, and R for reduction. So gain of electrons equals reduction. A phrase that might help you remember that, okay, as far as oxidation and reduction of reactions go, is Leo the lion says grr, all right? And you can see here, a loss of electrons or oxidation equals a gain of electrons or reduction. Okay, think back to Newton's laws of motion. Okay, for every action, there's an equal and opposite reaction. It is true with everything you see around you. Okay, for every action, there's an equal and opposite reaction. So if an atom is giving up electrons, that means those electrons have to be gained somewhere. They don't just float about freely, they don't just wander around, they have to be gained somewhere, okay? If a atom is gaining electrons, that means somewhere there had to be an atom that gave up electrons, okay? So if there is a loss of electrons, something has to be gaining them. If there's a gain of electrons, something had to lose them to begin with, all right? Hopefully that doesn't confuse you. Hopefully you can figure out what I mean by that. So, agents of a reaction. So you have the oxidizing agent, okay? This is the first one we're going to look at. This causes oxidation by accepting electrons from the other reactant. And then you have the reducing agent, which causes reduction by giving up electrons for the other reactant to accept. So the oxidizing agent opens up, basically opens up the channel for the other atom to accept the electrons, okay? The reducing agent opens up the original atom. Okay, we're going to go with atom 1 and atom 2. Okay, atom 1, atom 2. So, with the oxidizing agent, it opens up atom 2 to receive the electrons. Okay, and the reducing agent opens up atom 1 so it can lose the electrons. Okay. So, oxidizing agent opens up the atom that's going to receive the electrons. Reducing agent opens up the atom that's going to lose the electrons. Atom 1 and atom 2. Okay? Hopefully that doesn't confuse you. I was afraid if... Sometimes I get confused if I don't use my hands and figure it out. Okay? So hopefully it doesn't confuse you guys too. Alright? The reducing agent is oxidized and the oxidizing agent is reduced. They do the opposite to each other, okay? So if you have the oxidizing agent, it's going to reduce. If you have the reducing agent, it's going to oxidize, okay? They do the opposite to each other. That's very important to remember, okay? Do not forget that. If it is an oxidizing agent, then it's reducing. If it is a reducing agent, then it's oxidizing. It does the opposite every single time. Okay, every single time without fail, it does the opposite. So if you get a question that says something about the oxidizing agent, your answer is going to be something about the reducing agent, okay, and vice versa, okay? They always affect each other in the opposite direction. The reducing agent does the reducing, but it does not get reduced. That is important to remember, okay? Just because it's named the reducing agent doesn't mean it's getting reduced. It means that it's opening up the atom to allow reduction to happen, okay? But it is not being reduced itself. Oxidation and reduction occur simultaneously. So, like I said, for every action there's an equal and opposite reaction, okay? If oxidation is taking place in one atom, that means the other atom is automatically experiencing reduction and vice versa, okay? When one substance loses, sorry, typo on my part. When one substance loses electrons, the other must gain them. The electrons do not disappear, okay? I've already addressed this in this video, but the electrons don't just, gone, float into space. They have to go somewhere. They have to connect to something, okay? So if something is oxidized, another atom is reduced. If an atom is reduced, the other atom is oxidizing, okay? It's happening at the same time. Those electrons, they don't just float about freely. They're being exchanged equally at the same time. Redox reactions tend to occur in the direction that produces the weaker oxidizing and reducing agents. So, think about yourself here, okay? You tend to like the path of least resistance, right? You tend to like the thing that is going to use the least amount of your energy, okay? That's just human nature. We tend to look for the easy way. We tend to look for the easy route. Well, elements are no different, okay? They are going to react in such a fashion that they're not putting out all the energy that they have to put out. They're going to react in such a fashion that they're going to produce weaker because it doesn't use all of their initial energy, okay? So, atoms are no different than you. They want the path of least resistance just like you would. All right, oxidation numbers. Sorry. Oxidation number. This is the charge an atom is assumed to have in a particular ion or compound. Okay, so it looks, is it charged positively? Is it charged negatively? Is it a neutrally charged object? Okay. And that charge, if you remember, we've talked about that charge is all based on, you guessed it, the electron count. okay? If there's an excess of electrons, then there is a a negative charge. If there is a deficiency of electrons, there's a positive charge. And if both the electrons and protons balance out, then you're dealing with a neutral charge. Okay? So they're the result of assigning valence electrons to the more electronegative element, giving it a negative oxidation number. So when scientists study, sorry guys, it's really hot in here. My air conditioner is not putting out like it needs to be for this heat that we're experiencing. So, anyway, when scientists are dealing with elements, they're trying to determine what one is, as far as oxidation numbers go, they're going to look at which one is more electronegative, okay? Which one already has more negativity in it versus more positivity in it, okay? The less electronegative element is given a positive oxidation number. So the one with more electronegativity is assigned negative. The one with less electronegativity is assigned positive, all right? Rules for assigning oxidation numbers. I'm just going to kind of go through these with you guys. We're not going to work with them too much as far as me giving you elements where you have to determine if what the oxidation number is for those things. But I do want you to at least have it in your notes. I want you to be a little bit familiar with it so you've at least heard it and you can maybe go, oh, I kind of know what they're talking about if you ever watch a video or hear somebody say something, all right? So, rules for assigning oxidation numbers. The oxidation number of any uncombined element is 0. Okay, so if it's just one element all by itself, that oxidation number is 0. When you start getting into combined elements, okay, like you just have oxygen by itself, the oxidation number would be 0. You have H2O, then we're going to start looking at how oxidation numbers get assigned to combined elements. So the oxidation number of a monoatomic ion is equal to its charge. So monoatomic, that would mean it's just one atom, but there are multiples of that atom, okay, like O2, okay? And that is going to be equal to the charge of that atom. Is that atom, is that combined element positive? Is it negative? Hydrogen in its compounds is usually +1 except in hydrides. So H2O, hydrogen would be given a +1. Oxygen in its compounds is usually given a -2. Halogens in their compounds are -1 unless bonded to a more electronegative halogen or oxygen. And then you have your alkali metals and your alkaline earth metals and aluminum, okay, because aluminum is a derivative of those. But in their compounds, they have positive oxidation numbers equal to the number of valence electrons in the neutral atom. So if the neutral atom has, let's go with 3 valence electrons, just for argument's sake, then their oxidation number is going to be positive 3. The algebraic sum of the oxidation numbers of all the atoms in a molecule or polyatomic ion must equal the charge on that particle. Like I said, I just want you guys to be familiar with those and just have a little bit of basic base knowledge with them. I'm not going to assign them to you. I'm not going to have you practice them while you're at home because it's something that is better taught if you can be, I don't want to say you have to be here to learn it, but for most people it's easier to grasp if you can be there learning it from the teacher while they do it. So, oxidation numbers in redox reactions. So oxidation is a process in which the oxidation number increases or becomes more positive. Reduction is a process in which the oxidation number decreases or becomes more negative. So in oxidation, you're dealing with more positive. In reduction, you're dealing with more negative, okay? And one way I remember that is reduction kind of sounds like something's decreasing anyway, so I'm dealing with a more negative oxidation number. Reduction is a decrease or reduction in the oxidation number of an element, okay? Basically, like I just said, it's decreasing, okay? And I remember that by thinking of the word reduction. Using oxidation numbers to balance redox equations. In a balanced redox equation, the total decrease in oxidation numbers must equal the total increase in oxidation numbers. Okay, and that's not a typo. It is supposed to say that. So, in a balanced equation, okay, we did balanced equations all the way back at pretty much the beginning of the year at this point. But the total decrease in oxidation numbers has to be equivalent to the total increase in oxidation numbers, okay? If it goes down by 1, it has to go up by 1. If it goes up by 3, it's got to go down by 3, okay? They have to be equivalent to each other, or else they're not balanced. Strengths of oxidizing and reducing agents, just some, a look at how some elements behave with them. Zinc is typically a strong reducing agent because it easily gives up electrons. Zinc doesn't, it's not personally attached to its electrons, it gives them away freely, okay? And then halogens and the paramagnetic ion act as strong oxidizing agents, okay? They're going to try to take them in as much as possible. A strong oxidizing agent readily acquires electrons in a redox reaction to be changed into a form that is a weak reducing agent. Like I said, they are going to seek the path of least resistance. They are going to seek the way that will make them have to do the least amount of work, all right? So a strong oxidizing agent is going to take in an effort to put out a weaker reducing agent, and vice versa, okay? Any reducing agent may be oxidized by an oxidizing agent stronger than itself, okay? So the reducing agent, if, just for argument's sake, the reducing agent has an oxidation number of +1, any oxidation agent that has a oxidation number of higher than +1 has the ability to oxidize that reducing agent. All right, I wanted to make sure that I told that to you right, because sometimes my brain gets ahead of my mouth and I say things the way they shouldn't be said. Anyway, that is our last note for the first section of chapter 16. Again, get your notes down, keep up with them, all right? I am going to be taking them for a grade. If you have any questions about anything that I talked about, please shoot me an email, send me a message on the LMS. If I have to make another video to explain something better, I will. But I want you guys to be able to get this, okay? Remember, oxidation, reduction, all right? Oxidation is a loss of electrons. Reduction is a gain of electrons, all right? And if one is losing, there has to be one somewhere that's doing the gaining, all right? Have a good day, guys. I miss you, and I'm praying for you.